You can just go up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You can also get from the chart title, get from all this stuff. Yeah, also, I'll show this again real quick. You got all these options, you got so many cool things, it's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everybody, we're currently live. Who's all here? Anyone here with questions right now? What questions do people currently have live on the internet? So do we have anyone here? It says we got a few viewers. So let's see if people have questions. You can ask about any question. Let's just put a big question mark on the screen right now. Let's just go here and go. Question mark. It's Friday. So people are... Someone joins the stream, you're like, why is there a question mark on the screen? Why is there just a question mark right there? Who has any questions? I'm wondering, I'm going to do some tests right here. I'm wondering how this is the camera. We could do like a full screen. So, so I'm just playing around with the camera settings right now, or the Streamlabs settings to see how the resolution on the camera is. I'm gonna check that later on the video. So whoever starts this video is like, what the heck's going on right now? Are we following the same format as exam 3? That is correct, Master, right there. We are doing that. So good to have you here. Master, I've seen you in the chat before. We are gonna make you a mod. So we are following the same format. We're gonna average it with the quizzes. Now, I don't think there'll be a curve on exam 3, and I'll be posting my sections. I don't know if you're in our section, because we were talking about this yesterday too. You might have missed it. But there's a curve on exam 2 after we averaged them. We put a 3-point curve on there, and I'll be posting scores later. Just been meetings this morning, everything. Oh, you're in our section? Awesome. Yeah. So now you're a mod. Sorry. I just don't know the name when it's that, which you're allowed to have any name in the chat you want as long as you're, yeah. So sometimes people come in here and they make random comments and then we remove them. But as long as, you know, I try to make sure the mods aren't removing random, because anyone can have any name in here they want. They're allowed to do that. So that way, if you want to have your real name in here, you can. If you want to have any sort of name you want, that's fine. Everyone's allowed any name they want. So, well, I mean, you know, within the rules of names. So, but with that right there, we will be averaging them. We will be doing that. That is true. We will be averaging your quiz score. So it's very important. Do you have any questions on the quizzes? Are you working on any, like, the chapter quizzes? Any of those right here? Streamlabs. Let's see. We go over here to any questions you guys have. Can we go over the tips? Yeah, do you want to do the tips problem? Let's do the tips problem. The tips problem, and this could be on the final because it's a chapter 14 question. For the tips problem, the big equations to know are the mean for the distribution of sample mean is equal to the mean. The standard deviation for the distribution of the sample mean is equal to the original standard deviation over the square root of n. These are the key things to know right here when we work this problem. So when I copy this problem here in just a moment, I want you to try to identify this notation. Now, these are the things we are solving for right here. We're solving for those. We're going to use the mean, which is like, what is your average tip? Like, if you work at a restaurant, that's awesome, Jeff. We can do whichever problem you want to, Jeff. We're going to do the waitress problem, the tips problem again, and then we will do, if you have any sort of problem. Good to see you here, Jeff. We were talking about video games yesterday. Hopefully you got some video game time in. So, I mean, everyone's got time for video games right now. So hopefully you got some class time in. And I've got really good news on all the Twitch stuff. It looks like the interviews are a go, and I'm even putting word out there to see if we can get, like, anyone who wants to do it. Like, if anyone knows anyone, if you're watching this video, I should announce it during class. But if you know any, like, we want to do, like, sports interviews, you definitely did. What'd you play last night, Jeff, as I pull up the waiter or waitress problem question? What was your games of choice last night? So we'll make Tyler a mod, too. Tyler, you are now a mod. So, what was your game of choice? I'm already saying, I think you mentioned Ace, it's not Ace Ventura, that's Pet Detective. Ace Attorney, I think you mentioned Ace Attorney, or someone else did. But are those like story games where you have to like make the right choices? I always see like IAQs or something in those games. So I've seen some. I'm focusing here. Assembly, distributed, assembly mean. Okay, we're going to the homework, I believe. Let's do it. I just played some GTA Classic. The flight one again. Yeah, let's do the flight one. We'll do So I think we have the flight one, and then if Jeff has a question, we're going to do the waitress problem right here. Did I find it already? I have found the waiter-waitress problem. So here we go. Here's the waiter-waitress problem right here. And let's give it a shot. So we're going to grab the data from this. And we always have to remember that whenever we work these problems, we need to know the notation. So the biggest thing whenever you're working these problems is know your notation. I say it every day. It's you got to practice. You got to be like, what does it all mean? What's my notation? We're going to just do one more screenshot of this to make it nice and big so everyone can see in the video. I'll go one more time. Oof, it's too big. Nah, we got it right here. We're just going to grab the top part of that because that's really the main part of it. So we always practice knowing our notation. We get a problem like this, and then we say, okay, can we figure out all the notation in the problem? We go to our blank sheet of paper. We put the problem in, nice and big and easy to see. So here we go. We lose our pen. We really lose our... There's the pen. It's like, where'd the pen go? And here we go. So we have this right here. I need you guys to help me out. It says this is a mean of this. What is that in notation? It says a waiter believes that the distribution of his tips has a model that is slightly skewed to the right. So it's a little bit skewed to the right with a mean of this. What is the notation for the mean of this? What is that? I need someone to help me out here. Million-point question in the chat. What is the mean? What is that in notation? Who's got a guess at it? We were putting it earlier. It's in the channel name. What is the mean? Any ideas? Have I stumped everyone already? Any ideas? So it's the mean. Think of moo. I don't want to say it. I want someone to say it in chat. We know someone knows it in chat. We got a few people watching right now. It's the mean. It's the moo. It's the population mean. It's a symbol for that. We just had it up a moment ago. I'll give you some hints on the screen. Always know your notation. This is the way when you're taking test problems, you have to narrow down the notation because you get a formula sheet. It's something on this screen right now that we are talking about right here. This is the known mean. Any ideas? It is mu. I'll take that right there. It is mu. Oops, that's not the highlighter. I thought I had the highlighter selected. Look at the top. Does that not show that the highlighter is selected? Now the highlighter is selected. It is going to be mu. So mu y bar is actually what it's going to be equal to. This is kind of what we're solving for. Great questions right there, Jeff. We are solving for this. This is what we're interested in. We want to know the mean for the sampling distribution. And the mean for the sampling distribution of the sample mean is equal to the mean. So the problem actually tells us the mean. It's saying the mean for this waiter's tips is equal to this. So this is mu. And what do we know? This thing is having fun with me. We know that this is equal to mu, and then we know that since mu y bar equals mu, well then we know what mu is. So since we know what mu is, we know this is equal to 10. We know that right there. So we know what mu y bar is because we know what mu is. So then we get this right here. That is the standard deviation. I'll give you guys this one as a freebie. That's going to be sigma, and sigma is going to go over square root of n, and that's what we're going to get over here with SD y bar, because we're solving for SD y bar. We're interested in the standard deviation of the distribution of the sample mean. And listen as I say it, the standard deviation for the distribution of the sample mean, the mean for the distribution of the sample mean. So those are kind of big concepts right here, and it's what we're trying to draw out. We're saying, what would they expect on average for the distribution of their tips? And that's this. And what would they expect on average for the distribution of their sample, the variation in the distribution of their sample tip? I'm going to repeat that. What is the mean they would expect for the distribution of their average tip? And what is the standard deviation they would expect for the distribution of their sample average tips, of their average tips? Whew, it's a lot. It's a big concept. I understand why people get confused on this. It comes down to notation and understanding what's going on right here. It gets a lot to say, especially when you're looking at mean of y bar. That's the mean for what sample tip we would expect on average. The mean of the average sample tip distribution. A lot going on right there. I understand, a little bit confusing. So we're going to take and plug in the rest of these numbers into here. And the standard deviation is just a measure of variation. So all it's going to do is tell us how variable their average tip is, like the distribution of their average tip, the variation in it. So we go right here and we put 50. And then we start solving. and go to the calculator. Go right here, go 50 square root 6.50 divide by that. That is now, so it's 0.919. There's that right there. We take this, and now we got to go to Mr. David M. Lane. So we're going to go to David M. Lane website, and we take that answer we just got, and we're going to put it into there, not that answer. We want the new standard deviation. The new standard deviation, there's the mean, and then we go over to here. We put in the mean of 10.10 and the new standard deviation. Now, I think this is where people get stuck is, one, the problem doesn't ask you to solve for these first. It doesn't say find the mean, find the standard deviation, but you have to. You have to find the mean and the standard deviation, and then you have to do a little bit of math. If you want to make, I need someone to answer in the chat for me, if you want to make $650 off of 50 tables, what average tip would you need? You would need an average tip of this to make $650 off 50 tables. What average tip would you need to make $650 off 50 tables? Who knows? Who knows? Does anyone know what average tip you would need? What average tip would you need to make $650? 13, Tyler. It's a great job. Both of you right there. So it would be $13 because we're going to divide 650 by this right here. And that's what we need. So then we go back to David M. Lane. We copy paste. And we're going to go above 13. And if you notice, we're going to go over here. Above 13. Wow. That's really highly unlikely. I hope I did everything correctly. So that's very unlikely. And yeah, I guess it looks like about that. Does it like it? Woo, that was a very small decimal percentage. So we got that right there. Exactly. Nice job, Michael. I'll make Michael a mod here too. And so now we want the best 1% of such weekends. So we go over here. We put the best 1%. This is where people often make a mistake too. Do you think a really good weekend for a waiter would be making $12.23 or $12.23.8? That would be a really horrible weekend. You have to remember they waited on 50 tables. So on 50 tables, their average tip was this. So they made $611.90. So remember, this right here is the average tip. This is a distribution of mean tips. So they would expect their mean tip to be $10.10. And then this is 1 standard deviation above, 2 standard deviations above, 3 standard deviations above. So you can look, this is about 2.3 standard deviations above. And so it's kind of unlikely. I mean, it's pretty unlikely. And so we put this back over here. This is after we times it by 50 because they waited on 50 tables. And we hit enter. And of course, it likes it. You always get a little worried when you hit enter right there. And I see Sydney has a question about the flight one again. So we can do the flight one here. So let's talk about the flight question. Great job. Great job working on all these. I know everyone's working really hard. Someone told me they worked these problems for 7 hours yesterday. I was like, whoa. And I really appreciate that. I know lots going on in the world. Just take some time. Just be like, okay, I'm just going to work some stat problems. Everyone, I am busy working stat problems. Just put that up. Busy working statistics. So I think it's a confidence interval one. Sydney, correct me if I'm wrong. Found it. It is confidence intervals. So it is a confidence interval problem. So for this one right here, we're looking at, it's still quantitative because it's percentage. We're looking at like the percent of time flights are late. And we have right here, awesome, Sydney. Great to have everyone here. And we're going to check all the assumptions. Are they random flights? Less than 10% of all flights? Are they independent? I think all the assumptions are pretty much met right here. There's no good reason to believe that any of them are not met. This does look pretty normal. That's not really an outlier. It's pretty normal. So that's the nearly normal condition. Now here's where people get stuck, and let's go grab, and once again, well, the good news is they've told us the notation basically. So we don't have to worry too much about notation right here. That is the least of our concerns on this problem. This problem already has the notation written for us, but here's where people get stuck. Instantaneously, when we're doing t intervals, I'll give that away. When we see this and we're doing a t interval, what should we solve for instantaneously? So when we're doing a t interval, there's something else we need to know. And if we're doing a one sample t, we can solve something really quickly with that. So with that thing I just highlighted right there, since this is a t interval, What are we going to use n for to get very quickly? So it's good practice. Every t has with it. You got it, Sydney. Nice job. 1,000,000 points. Everyone in the chat gets 1,000,000. So df equals 71. And I still love, for those who didn't know it, maybe they saw it yesterday. How many points do I have now? I changed my points if you were in the first class. Let's see if the commands still work. So I need to learn more about Streamlabs. I'm going to be looking up a lot about this. So if you notice, we got the degrees of freedom. Degrees of freedom are just n minus 1. So the degrees of freedom equals n minus 1. That's how we solve degrees of freedom right there. So the degrees of freedom are 71. I need to talk and chat more and get more points. You get like 5 points if you talk every 5 minutes. So you get points, stay here, talk, say hey. Let's go get our stat distributions t. So let's take a look. Stat distributions t. And let's bring it in here. So we want 71 degrees of freedom. And we want 99% confidence. If you notice, I just wanted to make it very clear why I'm doing this. I'm putting 99% in the middle of the curve. So you can see my curve is 99%. There are other ways. You could just put 1% and put 2 tails on it. So if I do 2 tails at 1%, this is the same value right here that I just had a moment ago. That 2.647 is the same if I go here and I do 99 and I do it in the middle. So 2.647. It can be negative or positive, doesn't matter, because we're going to do, and we can do carbon monoxide next. You got it. 2.647 right here. So let's drop that into our worksheet. All right. So we know the t statistic now, and I think we're pretty much good, is that the t is going to be 2.647. So that's the, you got it, Jeff. 2.647 is the t statistic. Now we just need to know our equation. Once again, we'll be giving you these on the test. Y bar plus or minus t, there's the t, s over square root of n. And so we get here, y bar is 24.7500 plus or minus the t of 2.647, and then s is 2.63502, and then over square root of 72. And that should have it right there. I love it. Love people checking their points. You almost have as many points as me. Great job. So, hey, Brian, when do you plan to... I can do chapter 15 after this, John, if you want. So we can do that. John, you're video game, John, right? Do you play video games also? Is that the right John I'm thinking of? So there's a John I would talk to this semester all about video games. And then you start playing more Ori. So I started it, and I just haven't been playing it nearly enough. You guys want to make sure I don't put in a typo right here. 0.822. That's going to round to 0.822. We were talking about video games at the start of the stream. Video games. Everyone loves video games. I think that rounds to 0.822. There we go. People need to play Celeste or The End is Nigh. Those are great games. Oh, you're Misty Scotch. That's fine. You're still allowed. Yeah, there was a John who came to Office Hours 2 days in a row. You're on a roll. So good to have you, Calzone. Yeah, we could do that one. We could do, I think, which one's next? We got carbon monoxide next. And then, so we can do the carbon, we're going to do that chocolate chip one next because it's in this thing. And then I'll do carbon monoxide. And then we'll do chapter 15. Which I think, so yeah, we're gonna do the chocolate chip one, and then we'll do the carbon monoxide. So you got it right there. I'm just adding and subtracting these numbers right now. That's got that. That's the plus, and then let's go out of here, and let's go over to here, and I need that margin of error. Dang, I just copied over it. 2 decimals, and then let's check our numbers. Always check your numbers. So we need to do the minus. There's that. And we got that in there. And we round up. Interpret this interval. We always try to do this without looking at it. I am 99% confident the mean percentage of time that a flight is delayed is contained in the interval blank to blank. So we can be 99% confident that the true mean monthly percentage of delayed flights is in the interval. Yep. this one right here, we are 99% confident that the interval contains the true mean percentage of monthly time flights are delayed. Has that got it? If I selected everything, I think we did. Check answer, got 100%, good. Okay, chocolate chip question is next, because that's in this chapter. I know you already did the principal problem. Yeah, I think we did it yesterday. So Julian, if you look at yesterday's video, I did a lot of problems. Did I do it right between classes yesterday? Look, I did some problems between class and just skim around. So right between classes. If you can't find it, email me. If you're in our section, we've got it open for a good bit of time. So, and we could also do it again later if you want. So if you can't find it, I'll do it again later. Here we go. Here's the 100,000 chocolate chip cookie trial, something like that. Okay. So in this problem, we're given data. So here's the biggest thing with these problems. Whenever you get a problem like this, use jump. Jump's going to make your life so much easier on these problems. So you want to go here and you want to copy the data to the clipboard. And you'll notice this does not have column names. That's very important. So if you're watching this right now, be like, does that have column names or doesn't? You just do Command-C or Control-C on a PC, Command-C on a Mac. You go over here to jump, and we're going to go ahead and jump into jump. We're going to skip the tutorial, and then we're going to go to File, New, Data Table. Oh, it's good to see you, Caleb. Thank you so much. Hope you're having a great day, too. And we're going to paste this in here. I'm just going to go paste. And please notice that you can paste improperly. The one on the right has the column name at the top. That's bad. And you want to make sure when you paste, you either paste or paste with column names. You do not want to paste with column names right now because that would put the first thing in the column. That's wrong. You'll notice here that this one right here has no name. That's all right. We could just call it, chips or something like that. But we don't want to paste into the column name. You want to paste in the column name if there was a column name, but there is no column name, so we're not doing that. From here, we're going to go to Analyze, and we're going to go to Distribution. I think carbon monoxide is next. You got it. We're going to do chips, and then we got this right here, and then we go to stack, and boom. Now, a lot of these problems might have you kind of change the bin widths. So whenever you make your histogram right here, you can change this by clicking down here, double-clicking on it, and changing what this looks like. So you could put it going from 1,000. This one doesn't ask for this, so don't worry. I don't think it does. And then you could do it in this. This will change the way it looks. This one might. I'll take a look here in a moment. But you can change this right here by double-clicking it and changing it. So you have to look at how yours looks sometimes if they give you examples. Okay. Check the assumptions for the inferences. Oof. These are the tough ones. Oh, it does give me shapes. So here we'll go to the shapes. This is the easy part of it. If you look at our graphic right here, we have 900 to 1600 going up by 100. And so we're going to double-click on this. We're going to start at 900, we're going to go to 1600 and go up by 100. And now it looks like that. So if you notice, it might have been 700 to 1400, but you can tell by the data right here that it starts at 1054. So this would be wrong because this would be in like the 800s. This is in the 1000s, which is where this is. Also, my histogram looks like it perfectly. If I put the other numbers in there, the 700 to 1400, it's not going to look like this. It's going to be off center. So if you notice, that's not the way it should look. I'm going to bring it back over here. So you can do it this way, but this would be harder to do by hand to get it just right. Yeah, looks like we did it. So the answer is this one. These are the easy questions, the ones that, you'll get the right answers on if you do them correctly. It's definitely unimodal and symmetric. So it's not bimodal. It's not asymmetric. Yeah, so it's unimodal and symmetric with no outliers. So we meet the nearly normal condition. Here, I'll go back and do the first one because we didn't do that one. Check the assumptions for the inferences. Oh yeah, this bag of chocolate chip cookies is less than 10% of all the chocolate chip cookies. And we would assume that, someone can assume, the data are from a random sample. Okay, these don't really make sense because you can't assume since they're less than 10% that they're independent. The data are from a random sample, so one can assume they are independent. Boom. So that's why I always lump together the random and independent, hoping we can do that one next year. We've got carbon monoxide, and I think we'll do that one next year, Michael. So we've got here the data can be random because they're independent, so they're random, so they're independent. Pretty much like that. And now this is the easy part because I want to point something out. When you do this in jump, and anytime, everyone just pause a moment. Whew. Anytime you get data, you wouldn't really assume it. You would look at it. No, great question. Oh, no, sorry. Hey, John, let me make you a mod. Streamlabs is being stupid. What did it... Why did it get mad at that? Oh, I know why. It was, hey, Glizza. It was literally this word right here. It thinks you're trying to, like, cheat the system. That's so weird. I've got high settings on here in case someone uses, but you're a mod now, John, so that'll never happen again. Or it can't. I mean, well, nah, it might be able to if it, I don't know. we won't test Streamlabs. But that will stop that from happening. So, we have right here created a 95% confidence interval for the average number of chips. If you were given a different percent confidence, you could go here to confidence interval and choose something right here. So you could go here and create a 91% confidence interval, and it would create a 91% confidence interval, the lower and the upper right here. So we just take this interval over here, 11714. That's the lower. And then we go to the upper. And the upper is 1336. I think that's it. No, 1337 because it rounds up. It wants one decimal, right? That all rounds up. So 1337. So what does... Give me a phone. What does the evidence say about the company's claim? So this is on average for a bag of chips. It's not that each individual bag of chips will have this. It's on average. Because the interval is entirely above, okay? Because the interval includes, nope, because the interval is entirely above. It has to be A or D. It means the number of chips per bag is likely more. The mean number of chips per bag is likely more. However, the normal model predicts that a small amount of individual bags will have fewer than. That sounds right. Yeah. So answer A is wrong because it says that every bag will have this. But I want everyone to tell me, what are we making a confidence interval for? We are making a confidence interval for the what amount of chips in the bag. We're making a confidence interval for the, like, is it for each individual bag of chips or the what amount of chips in a bag? This confidence interval is being made for the true something. The true who knows. It's a 95%. You got that right. It's for the true what, though? You got, Jeff. You got this. The true, we're trying to say I am 95% confident. The true blank of chips in the bag. Not one individual bag of chips, but for like all bags, like if we average them together, the true, like when you look at the interpretation, I am 95% confident. The true, someone knows in chat, million points who knows. Close, Jeff, you get the million for that still. This one is true mean. You're super close. Last chapter, or the chapter before with confidence intervals, was true proportion, where this one we're analyzing the true mean. So in this chapter, and I'll show you real quickly here with the notation on it, in this chapter, when we do this, and this is a good review, when you have y bar plus or minus t s over square root of n, the first thing right here tells you what you're analyzing. So the first thing right there is what you're analyzing, and the previous chapter was p hat plus or minus z p hat q hat over n quantity square root. Now I want us to look at the first one and the second one. In the first interval, you have the sample mean, and the sample mean is trying to estimate an interval for the true mean. Now in the lower one, number 2, you have the sample proportion, and you're trying to estimate an interval. I want to see someone say in chat, I know someone knows it. In the second one, you're using the sample proportion to estimate the what? In the second one, you're using the sample proportion to estimate the... Yes, so say the answer again, who's got it? The second one is using the sample proportion to estimate the... Someone knows in chat, I know. I'm going to give you hints again, right? The first one is using the sample mean to estimate the true mean. The second one is using the sample proportion to estimate the... Someone knows it. I'm going to wait till someone knows it. I've got one more minute in me still. I'll repeat it. You ready? Million points in the chat. First one uses the sample mean to estimate the true mean. You got it, Jeff. You got it, Jeff. Great job. The true proportion. So once again, the first interval uses the sample mean to estimate the true mean. Hey, good to see you, Adam. The first one uses the sample mean to estimate the true mean. The second one uses the sample proportion to estimate the true proportion. So this is why we'd say I'm 95% confident the true mean amount of chips in these bags is contained in the interval. So does that mean all bags of chips will have this? No, it doesn't mean all bags of chips. It means on average, your bag of chips will have this. Like if we were to look at a whole bunch of bags of chips. So that's the wrong answer. Good thing. And the normal model predicts for individual bags that they'll be lower. And we got it. Good job. Okay, I think the carbon monoxide one is next. Yep, it's pretty tricky. No, Jeff, that's the reason I pause on a lot of these things. These are common mistakes a lot of people make. So it's really good to make these mistakes because then you'll learn, okay, okay, that's the sample proportion, that's the sample mean. The sample proportion estimates the true proportion. The sample mean estimates the true mean. Because the t-scores we risk on the one-tailed or two-tailed, how do we determine which to use? Here, let me do Jeff's question real quick. Then we're going to go over because we were just doing confidence intervals. So, or Adam's question. Is this a testing question or a confidence interval? So on confidence intervals, I always build my confidence intervals by doing the between. So whenever you make a confidence interval, use the between amount. You could also use the two-tailed and do like 0.05, and this would be a 95% confidence interval. Now, when you're doing statistical testing, you need to know, is it does not equals, greater than, or less than? So if you notice here, this would be a does not equals test, two-tailed, greater than, shade to the right of it, and less than, shade to the left of it. Now it's changing what the number is up here, because we would usually just do that, but that would be the less than test if we landed at a t-score of 1.667. So when you're doing statistical testing, the question dictates what way you shade. Like the researcher says, is there evidence that it has increased? So then you would shade to the right of the t-score. Now when you're making confidence intervals, there's a lot of ways to do it, but usually I like to do it right here where I build like a 98% confidence interval with this t-statistic. So in the confidence interval, you use the t-statistic to make the confidence interval. You don't solve for the t-statistic. Different. Oh, yeah. So Adam, really good thing right here. I'm going to give you a link to this right here. You can use t-tables, but check out this link in the chat. This will make your life way easier because you can just put in the degrees of freedom and then you can put in the confidence level. So if it says something like 95% confidence and 25 degrees of freedom, there's the answer right there. Yeah, we'll do that. We'll do that one after. I think we got 2 more questions in the queue, Ivy, and then we will do that one. So great question, Ivy, and good to see you. Yep, that's awesome. Yeah, it's good practice. I think the carbon monoxide one was next. So correct me if I'm wrong. I think we have the carbon monoxide one. So let's do that. And then we've got Ivy in the queue. I think we have 2 more set to ones, and then we've got Ivy. And good to see everyone. So, yep, carbon monoxide one. Let's do it. That is chapter 14, sampling distribution of the sample mean, right here. Okay. And I think the pregnancy one was next, maybe. So, which is also in this chapter. Whoa, found it. Okay. So for the carbon monoxide one, we have to know the formulas on it. Let's copy our work down, and let's take a look. Okay, there's the work. There we go. Zoom in. Okay. So carbon monoxide emissions for a certain kind of car have a mean of this. So if this is the mean, yep, we can do that one here in a little bit. So this one right here, it has a mean of this. With a mean of this, what is this in notation? If this is the mean, I need to see it in the chat. What is that in notation? Follow along. Who's got this? That is going to be what if that is the mean? 1,000,000 points. Who's first person to know? Remember, you get your Streamlab points by answering questions. So be talking every little bit here. You check your points. Mu, Tony, great job right there. It is mu. 1,000,000 points, Tony, right there. I'm going to give this one away. That is sigma. And then we have right here n. And then we need to know our formulas for this chapter. So it's going to be mu. It's going to be just mu right here. So it's just going to be just mu because that is the mean for all cars. And then that is the standard deviation for all cars. We're going to use this to solve for the mean of the distribution of the sample mean. And that is equal to the mean. And then we have right here SD y bar equals to sigma over square root of n. So now we're going to plug in our answers, and we go right here. And we go 2.971, 0.8 is right here, and this is 80. So let's go ahead and solve. We already know what the mean for the distribution of the sample mean is. And then we go 80 square root 0.8, divide by that. There we go. Is that right? I think it was right. We'll hope. And that's 0.088 0.089. 0.089, and the other one's the same as the previous. 0.089. So it's going to be normally distributed. That's how the distribution works. That's the central limit theorem in play. And we go right here. And the answer was, we'll copy that, we'll paste it into here. That's got it. That's rounded the correct way. And I think we've got it. Now, the reason it's normal is because even if this was kind of skewed, the sample size of 80 makes things more normal due to the central limit theorem. The central limit theorem states that the distribution of the sample mean will become more normal. Like if your original distribution is skewed, the original distribution of the sample mean will have the same mean. So it's going to have the same mean value. The mean is in the same spot for both of these. But the distribution becomes tighter. If you notice right here, it's going to become tighter by a factor of the square root of n. So it becomes more normal and tighter, and I almost drew it completely normal. It'll even become more and more normal as n increases. As n increases, it'll become more and more normal and tighter. So it's going to get more normal and tighter as n gets larger. And that's the central limit theorem in play right here. It's going to have the same mean at all times, but the standard deviation is going to get tighter by a factor of the square root of n. So the first one, the black one, is the original distribution. Then the red one is for like a small n, and then the space pen one is for like the 80n, which is large enough to make it very normal and very much a tighter standard deviation. So it just gets more normal and tighter as n increases. And so with a large enough n condition, then what are the odds? Oh, the odds of that are probably pretty high. That's why I extended it through the weekend. I'm so sorry. I hope that stops happening. But yeah, like every night. It's every night with my Pearson crashing. Sorry, my Pearson. I'm sure you guys know about it. So here we go. We're going to put the numbers in here from the problem. It's working right now. 2.971. Keep that in our head right here. 2.971. 2.971, and then the area between 3.0. There go the other one. 2.971, and the area between 3.1 and 3.2, I think it was. 3.1 is about here, and 3.2 is about here. So 3.1 is about 1.5 standard deviation. It's going to be about 7%. 7% is what I say. I say 7%. Ooh, could I have guessed that? That's very close to 7%. Would I have gotten it? I was trying to guess these yesterday. Wow, would I have gotten it? Would this be right? I said 7%. Top 1%. So top 1% is going to be... This is a tough one now. There we go, we guessed it. We'll go back and we'll show how to do that one real quick. Could have guessed that whole problem, maybe not the other one. Oh, thank you, Adam. So it's just, I've done these a lot. The top 1% on this curve right here is, did it really give it to me? It's closer to 3.2. Wow. I should have got that one wrong. That was a really nice round on it. I still haven't gotten my OJ. Just wait till I get my OJ. I'll be even better. But the answer looked to have a nice enough plus or minus in it that it gave it to me. That was really a nice plus or minus on my Pearson's part to give me that answer. The answer for the top 1% is this. So you can see here we just enter in the top 1%. We put in the mean, we put in the standard deviation, shows us top 1%, and we're good to go. I think there was another, we have the pregnancy one. We'll do one more 201 question, then we'll do a little bit of 474. Then, of course, we'll do more 201. But what were the other questions? You say the question now that you want me to do, it'll be done. One more 201 question we'll do, and then we will do more 201, but then I'm going to do a 474 here. But what is another 201 question that people have right now? Another 201. So ask it in the chat. I'll get some stuff loaded up right here. Another 201 question. I see it. The airlines, public relations with the yes, that one's tricky. So let's pull that one up here, Amber. Great question. And let's see here. Tree-based models. I'm getting everything. Okay. Basic. Okay, cool. I'm getting everything up and going. Sound files. There we go. Okay, I'm pulling up other things right now. Homework-based classification, and make sure I have it up. Okay. And then the pregnancy one, we will do that after. Let's do these both real quick. We'll do them both. So the pregnancy one is actually in this chapter. So I'm going to do the pregnancy one first because I can get to that one super quick. They should be a little later today because I had a lot of meetings this morning, and then I will start getting work on that. Thank you, everyone. I think everyone kind of knows busy times, and so I think it's in the other thing now. But I should have those up a little later today, probably closer to the evening. I'll be done with this, and then I'll start working on that, and then you'll get your test scores. That'll be awesome. So, and I'll have to look at how to upload a grade column, because I don't want to type them in manually. Oh, it's no fun. So let's go to chapter, it's the quiz, I think. Chapter 14, sampling distribution for sample mean. Replace question. Or is it the homework? Here it is, found it. Okay. So this problem is very similar. That's why I'm doing it next to the previous one. Then we'll do the airline one. Then we'll do 474. This one is very similar to the last problem we worked. Let's explain why. What we have right here is quantitative data, and we know the mean for women. So once again, since this is a known mean, we're saying we know this is true for women. We know the average pregnancy is this. What does it make it in the chat? It's like our third time practicing this. We know the mean is this. So this is what in notation? I know the mean for women is this. What does that make that notation? I know the mean for women is 266. I know this. This is true. This is the true mean. What does it make it in notation? Mu, Adam, you are right. That is mu, million points right there. So then what does this make this? If this is mu, the other one is what? It is sigma. So we're going to go over to David M. Lane and immediately put these in. We have 266. I think the other one was 18. We'll double check those numbers. But we know this. This is a review problem from chapter 5 right now. It's going to switch over. But this is a review. Good to see you, Jeff. You're welcome anytime. So 265 and 70. We want to go between those amounts. And there's the 11%. Wow, that'd be a hard one to guess. 11.01%. And that's rounded. And then the longest 25% of pregnancies, I might be able to figure this one out. I'll guess it as we do it. So the longest 25% of pregnancies is going to be right about here. It's like a z-score of 0.67 because I've done a lot of these problems, which means about 2/3 of that. So it's going to be about 278. Now we have to go over to this version of it, but I'm expecting it to be like 278.1, 278.1. And the answer is 278.1. There we go. So just because I've done a lot of these problems, I promise you. This is my redemption today. Just wait till I get my orange juice. So 278.1. We could have guessed it. Man, it's so fun when we can get these right via guessing them. Suppose an obstetrician is currently providing parental care for 40 women. The question has changed. So Adam, great answers in the chat. Oh, you got the notation. Million points, Adam, right there. So we've got 40 women right here. So this is where our notation comes into play. We know what mu is right now. Spacepen. And we know mu is equal to 266 and sigma. Already think about sigma. Mu, sigma equals 18. So we know these values right here, and now we have an n of 40. This is no longer individual women, it's for a mean of 40 women. So now we're going to do the distribution of the sample mean is equal to the mean. So I'll write that out just so you can see. It's equal to the mean, and the standard deviation for the distribution of the sample mean is equal to the original standard deviation of the square root of n. So we go right here and we plug in our numbers, and we get the mean of the distribution of the sample mean is equal to the original mean. This is equal to 18 over square root of 40. So the mean does not change. This is what we were seeing previously, that if we have a distribution here, so if it's normal, it'll stay normal, but it'll just get tighter the higher, the more n gets. So it'll get tighter and more normal, but the mean won't change. It's just getting tighter, and the tighter you're seeing is due to the larger n. Large enough n makes everything pretty much normal. That is the central limit theorem, saying two things once again, that the distribution of the sample mean becomes more normal and tighter as n gets larger. That's what you're seeing with that graphic right there. The original one is the black distribution, and then red has a small n, and then the space pen one is a very large n, making it even tighter, but the mean does not change. This center of this distribution right here, that center that I'm trying to keep the same, is because the mean is just the mean. It doesn't change as we get a larger and larger sample. What does change? The standard deviation. Also, the shape of the distribution becomes more normal. Central limit theorem. So, repeat things. Make sure we get them down. So we go here to our calculator, and we take square root of 40 first to calculate it. We copy that, we take 18, divide by it, and then we go right here. This is our new standard deviation. We go back to Mr. David M. Lane. We put in the new standard deviations into here. Remember, you can pause these videos and slow them down. And we're going to go here, and we're going to ask, I think, what are the longest pregnancies? Let's find out what the question is. What is the mean? Oh, we already got these things. 266, because the mean doesn't change. It's still the same mean. What's the standard deviation? Very long thing. What is the probability that they will be less than 271? If you watched yesterday's video, make sure you watch if it's less than or greater than. It'll trick you. So now we want to go less than 271. So we go below 271. Watch out, less than greater than. I think they switch it up sometimes. We could have maybe guessed that. So 96.05. Always like guessing the answers. So that's going to be 0.961. We cross our fingers. This is our redemption. And of course, we got it right. So there we go right there. We got redemption today on this question. So what do we have next? I think there was the airline one. Then we're going to go to 474. Let's do it. Let's do the airline problem. The airline problem. And that is chapter 15, airline problem. Okay. Was it in the right chapter? Chapter 15. How's everyone doing today? You're welcome, Julian. You're welcome, Julian. Glad to help out. Try and do as many questions as I can, help as many people. I know it's a lot harder now without Stat Lab. I mean, we've got Connor helping out, doing a lot of great stuff. But I like it when I come to these streams, and I know we might not have a ton of people watching, but as many people as we can watching. And we're also, let me put it in the chat again. If you've got a Twitch, come on over to Twitch. We're going to start streaming on Twitch. That's moderator. Let me go away from that. Okay. So if you have a Twitch, join our Twitch and follow the channel. And we are going to start doing some really cool stuff on Twitch, I think. So hop on over to Twitch, check it out. I'm going to keep promoting it. And either this week or next, or the coming week or the next, we're going to start doing some interviews, maybe some really cool stuff. And I'm excited. Maybe I could, I don't know. I wonder if I could hook a Nintendo up to it. I don't know. Maybe the capture, I don't know. We'll find out. But we want to do a bunch of stats related stuff, but I always think video games and statistics go hand in hand. So, if I can start talking about stats and video games and how everything goes, just toss follow. Thank you so much. Yeah, give it a follow. And if we can I'm looking to get as many people to interview as we can. So what I would like, and my goal right now is maybe Tuesday night, we do a big interview thing. And I'd love it if the whole university, as many people as we could heard about it and would watch it. So as many people as we can get and do some really cool stuff. I think we can do that through the university. I just have to look at, I think with the university channel, I think they'll actually partner us a lot quickly, and I have to look at the contract. So I need to double check all the contract stuff, because I think since I'm a university channel, they partner university stuff really quickly. Probably because they want education people involved. But I just have to make sure, because you sign a contract. But no, so I think maybe we could do it the old-fashioned way. What if we just did it the old-fashioned way and just we're just going to do it, get a bunch of people to follow us. But either way, I'm really excited. And if we do make money from this, it'll go back to students. That's the whole goal from this. So once we get monetized on YouTube, which should be happening, I've already put in all the stuff. But once that happens, any money we make goes back to students. So we're going to put it to tutoring. We're going to put it to pizza parties when we can all see each other again. But yeah. So let's see right here. And thank you. People have been putting timestamps in the videos. Once again, 1,000,000 points bounty on each of those timestamps. So if you put a timestamp with when Brian does a question, that's a huge help for people who come back and watch the videos later. A lot of people are like, oh, it's so awesome. I just click the timestamp, go right to it. Huge help, and we really appreciate it. So thank you for everyone who's been making this so much better. And it's cool. I can see when people sub to the Twitch channel. Yes, I see you right there, AJ. So, yep. If we ever see each other again, I'll be around. This'll end. This'll end. So we'll just communicate. See, that's why Twitch is more important than ever. We got to do it through the internet now. We got to communicate. How do you make a timestamp? After the video ends, you'll come back to the video, and you'll type something like 4208, and you'll type airplane problem. Now I'm not at, how far am I in? Yeah, it's about the time. So we started streaming. It'd be closer to this. You'd be like, Brian talks about Twitch. You'll type something like that, and that'll add a timestamp. It'll treat that time right there, and you can literally click that time, and it'll skip someone to this part of the video. So for anyone watching the video in the future, if they're like, oh, I want to find this problem really quickly, the timestamp, you just click it, and boom. And I'm going to try to put a lot of those timestamps in the descriptions. But if you're just working a problem, you want to just grab the timestamp, be like, oh, Brian solves this problem at this point. Just put a note like that in the video and put it under the comments. That also helps our interactions on the channel, and people are more likely, like, once we get monetized, the amount of interaction we have, the amount of likes we have on videos play a big thing on if YouTube starts promoting our videos, because YouTube will be like, oh, people are interacting with these videos, people are liking these videos, so they'll push it through the algorithm, and it just helps students, because then we'll get more exposure, and that means more follows, more likes, more everything. And I'd love it if we were the premier statistics channel on YouTube. Like if people were like, oh, I'm learning statistics from Stat1 at UTK. Like, yeah, that's what we want right here. We want to be the ones teaching, not that other people can't teach stats, but, you know, it'll just help our students and everything if we're, you know, because anything generated from it, if we were getting like millions of views, all that revenue would just go right back to students. So everyone would get kind of our help, and then our students would get the benefit of everyone getting our help. So I think that'd be awesome. Okay, let's continue on. This is the dream. And so we'll continue on right here. We have a national airplane. We're going to copy this. You know what we're going to do. We're going to make sure we know that notation. It's all about notation. You guys know I'm all about it, because if you know your notation, you can start to solve the problem. And then we're going to do a little 474 next. So we're going to grab this right here. We're going to copy it in. And there we go. So the airline believes they have a public relations problem. They're saying they rarely lose luggage. That's their claim. Her claims that those occasions where luggage is lost, 86% are returned on time. So I need you guys to help me out in the chat. You guys know I always need some help with these problems. I need to know what any of these numbers are. I need to know what those numbers are. Does anyone have any idea? I need at least one person to give me one number of what any of those things are. One of those is not important, and two of those will be used to solve something else. My brain's starting to turn back on again. So I'm like, I think I remember how to do this. I think one of those is like extra information, just a number. I think two of those will be used. Two of those will be used to solve for another thing. Maybe they're pretty close together, those two things. And then another one of those will be like a hypothesized amount. Like we're going to test that claim. So, you know, we're going to see if we can cast doubt on their claims. Does anyone have any ideas? Close. Good job right here. 24 is the extra number. 86 is going to be P naught. Good practice right there, Tyler. 1,000,000 points to both of you. So 86 is P naught because that's their claim. So this is their claimed proportion, what we're going to test. Great job, Amber, right there. So this is the hypothesized. And then right here, these are the ones people often forget in notation. People often forget X. I've noticed that. And this is N. X is the number of occurrences, and N is the number of total trials. So we see right here that we can get from X over N equals P hat. So X over N equals P hat is going to be the sample proportion. So the sample proportion right here is merely just 133 over 188. And that's going to be something like 70.3%. Nah, 72.3%. Let's check. I should have went with the first guess. So there we go. Pretty close to that. I might need to carry a decimal or two more. Nope, that's right for decimals for now. We'll throw this on there. There. Okay, so we know what P hat is. We know what P naught is. Now we need to know the equation to use. So if you notice, I'm not really following the My Pearson steps because I'm going to do the steps we do to solve these problems. The first step in solving a hypothesis test is to write your null and alternative. To write the null and alternative, you must remember the notation. A lot of people get tripped up on this. You have three parts. The first part is a population parameter. So the first thing you'll do is you'll always write a population parameter, then a sign, and then you'll do the hypothesized amount. We already know what the hypothesized amount is. So let me put this. This needs to be P naught for part 3. We already know what P naught is. So since we know what P naught is, we're just going to put 0.86 right there. The third part is a hypothesized amount. Now the second part is a sign, but we always say this in our class. The null has someone's saying it right now with me, the null has the equal sign. The alternative is going to be the direction of the claim. Now, here's the thing. This problem has tricked me. the airline would be happy if they had more than 86%. The airline would also maybe say it's not equal to 86%, but that could mean more than. So we're going to try to show evidence that it's less than 86%. So we're going to try to show evidence that it's less than 86%. And what is less than 86%? The thing we're investigating, the true proportion of time people get their luggage back in one day. Now, what I want to point out here is that these do not change. Those do not change. The only thing that changes between these two nulls and alternatives, between the null and alternative, is the sign. So when you practice writing this, do it in 3 parts. And moreover, when I usually write these out, the first thing I usually do is I just write my null. So practice writing your null. Always be able to write the null. So you'd say the true proportion of time that people get their luggage back within 1 day is equal to 86%. Notice how I'm reading it. The true proportion of time people get their luggage back within 1 day is equal to 86%. Read it as a sentence and watch. I'm going to read it. The null states that the true proportion of time that people get their luggage back in 1 day is equal to 86%. All I have to do to write the alternative is write the same thing, but change the sign in the direction of the claim. So that's the only thing I change. I want to make that as clear as possible when you write null and alternative, to just change the sign. Just change the sign. You can do less than. You can do less than. You can do greater than. You can do not equal to. That's probably the hard part of this question right here, Amber, is it has tricked me before. It's less than because we're trying to put doubt on their claim to say, no, it's not true that you get their luggage back within 86% of the time within 1 day. We're trying to say there's evidence that it's less than this. We're trying to say that the airline's not meeting their goal. Because the airline, if they had more than 86%, that'd be good for them. They'd be like, well, that's awesome. We're even doing better than we claim. And if it's not equal to, well, that might mean less than or greater than. So I wish the problem was more clear, but it should say, no, do we have evidence that the airline's not meeting their goal? It should say that, and not meeting their goal would be less than. So I think the question could be a little bit more clear. It has tricked me before. So it is definitely less than, unless I get it wrong today. But I'm on a roll today. I'm on a roll. Worked a lot of questions so far. And we have right here, part number 2 of it is going to be the equation for it. So the equation for this is going to be y bar minus, wait a minute. Okay, good. My brain broke. We were doing y bar a moment ago. We're doing not sample mean, we're doing sample proportion. P hat minus P naught over P naught Q naught over N square root. So I was doing a one sample means test there, and this is a one proportion Z test. I was like, my notation doesn't look right. Notation. All I'm going to do now is plug in the numbers. So please note that I am just plugging in the numbers we've solved for. P naught and Q naught are complements. So since P naught is 0.86, it's an 8 right there. This is Q naught is going to be 0.14. And then this is N down here, which is the sample size. And then this is the sample proportion. And then this is the hypothesized. And so that's going to give us the Z, which is how far away we landed. So the Z right here, and always practice your steps. Like, don't let my Pearson trick you. So now we're going to take 0.7074 minus from 0.86. We get that. I'll have to do it again. 0.86 times 0.14 divided by 188 and square root. And then we do this up here up top again. And there's the, wow, that's a very, very, very extreme Z-score, negative 6.03. Negative 6.03 is a very, very extreme Z-score. Put it all the way up here, negative 6.03. So negative 6.03 is extreme. Yep, we're right, but we're going to hop in there. Nope, we're going to do that next year, Ivy. That is the next thing once we finish this, and we're almost done with this. Great question, Ivy. The assumptions look to be met. Write the null and alternative. We're going to do less than, and then the Z-score, negative 6.03. I need to make this smaller. The p-value. The p-value is 0, and I can draw it out here. That's the next step on this. The next step is to draw your p-value. And which one are you working on, Ivy? Put the one you're working on in the chat. And so we want to do less than this right here. And actually, I did it way too quick, because here's the thing. We are so far off this curve right now. We are 1, 2, 3, 4, 5, 6. And this is why I know the z-score, I mean the p-value. I know the p-value because that is basically 0. You can do it in the calculator. Do this. I wish I had the thing that I can use the calculator on this right now. D and so on. Which part of D? Like if you can copy part of it into the chat, that'll help huge. You can do it in the calculator with normal CDF. And you want to do, you wouldn't really, there is an equation, but it requires calculus. So I wouldn't want to solve it. You want to do normal CDF. Do normal CDF this. If you go to normal CDF. Oops, and I didn't close the parentheses. So normal CDF right there would solve it. And that's going to be very, 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 very next to nothing. I do have a video on it. Let me put that in the chat. Here, whoa, that's like a transition screen. So there's a video on how to use the normal CDF. I spent so long making these videos. I was doing like over Thanksgiving break, and then like no one watches them. That's all right. That's why I want to monetize, because like, oh, I made these what I thought were really good videos. Everyone thinks their videos are good. Do the results cast doubt? Oh yes. The results cast doubt because, and that's the last step in the hypothesis test right here. So since the p-value is low, the p-value is basically 0. It's basically 0. Step 4 is reject the null. So I'm going to reject the claim of the airline. I'm going to reject the claim that they have returned luggage 86% of the time. I reject their claim. The p-value is low, reject the null. The p-value is low, reject the null. When the p-value is high, just let it fly. So does it cast doubt? Yes, since the null hypothesis is rejected. There we go. I think we got it. Boom. Always hold my breath. So we got it right there. We are good to go. We got 100. Awesome stuff. Just that's what happens when I'm not working problems all day long. Okay, so let's check it out. What's going on? Okay. So let's see. Define fit control so the AUC will be computed using train fit vanilla regression on the train model. Yes. Okay. Awesome. Now I'm going to pull up some stuff right here, Ivy. Really important stuff. And I'm going to kind of show you through this in the chat. And this is some really good stuff for 474. It'll only let me paste in half the question. Yeah. Oh, I can tell exactly what we're going on right there. So here, I'm going to put this. I'm going to show where this is at. And we should have this in here. So Ivy, I want you to find this file right here, and I'll probably, this is due on the, what date is this due? 7th? Or no? My brain just is not working right now. I want you to look at this on Tuesday. Good. I might need to send an announcement about this. Let me pull this up here in R. I should have showed this in class last time. This right here is the best thing in the world. What do we not have installed? Discretization, do parallel. That's awesome thing. So, yep, I'm on the good computer right now, so it doesn't have everything I usually use. So what we need to do, this right here is an amazing, amazing file. If you look right here, we've got different fit controls set up, and on 2.7, yep. So we'll still have a class period to talk about this. Right here, what you want, you said you want a fit control setup to compute AUC. Boom. This is what we were talking about yesterday. So this is the fit control you want right here. And this is why having this file right here is very important. So you want this fit control I'm putting in the chat right now. And this file is found under the data mining 3 using caret. So it should be under there under the modules. Let me see if it's under the modules. But just going there and taking the right fit controls is so helpful. I probably should practice writing them 1,000 times, but I know that the AUC one has the class probs equals true and 2-factor summary function equals two class summary. But the other one right here, this is what we were talking about yesterday, just does accuracy. So if you use this fit control, it'll just fit towards accuracy. And this should be, let me make sure it's here. So is the caret thing on here? I think it's right here. Using caret to, is this the right thing? Yeah, it's the using caret. It's here, Ivy. I'll show you. But I don't know if everyone's looked at it yet. I should have pointed this out during class. It's this right here. And I have the R file open. Does that make sense, Ivy? This right here, this is a huge help. If you go to this right here, you can go to this file. You found it? Awesome. And then you want to go to this one right here because this has all the code in it. And it's a huge help. It's so crazy huge. So maybe we'll clip this and I'll be like, hey, here's a big thing you should know while doing this assignment is that this has like so much help for using caret. Once again, I find it easy to just go in here and be like, okay, you know, you can look at it. The train control is set up with no method. We've got here, and I was talking about repeated CV. What did I just do? I clicked over the side. And so here's repeated CV, and that's going to do repeated cross-validation. So it'll do k-fold 5 cross-validation 10 times. And then we've got here just k-fold 5 validation. All this stuff right here. Here's splitting up data, so there's code on that. Tons and tons and tons and tons of help. Just making different models. So what you can often do is you can Google through here, search, you can Google through it. You can go to a k-nearest neighbors. So no k-nearest neighbors? Oh, in selection. Oh, I've got that. I don't know why. There we go. Here's k-nearest neighbor. This is making a k-nearest neighbor grid right here to just make the tuning grid for k-nearest neighbors. We go right here. Here's fitting a k-nearest neighbors model. Oh, yes. Oh, so Ivy, we're going to probably put out an announcement about that. Aileen alerted me to this today. I'm going to check my email, but maybe send me your answers. Don't put them in the chat so everyone, but maybe send them to me. But I think there's an issue. Aileen sent me an email just earlier, so I'm very sorry about that. I'm sorry. We're going to probably have to send out an announcement saying, hey, here's the right sanity checks for these things right here. It sounds like you might be doing it correctly. Did this help, Ivy, with at least where the fit controls are at and stuff like that? Do you have the right fit control now? Yeah, send me those. And I don't know if Alien's replied yet. I might have to reply to that later. But did I send that out? I don't know if I sent that. Right. Homework problem, mix and quit. Virtual Math and Stats Symposium. April 17th. I have no idea what this is. So, yep. But this right here is a huge cheat sheet for like the remainder of the semester. It's just, especially if someone hasn't done anything in, like coding wise, then this would be very hard to understand what's going on right here. But if you take a look right here, we've got vanilla logistic regression right here, which just means regular old logistic regression, which is predicting a categorical y variable. So the y variable here is categorical. We have here that we're including all the x's to make our model. Then we're going to take the training data, which is what we always do in predictive modeling, GLM for generalized linear model, and then we have the train control equals the fit control. We have to specify that beforehand, and then we have the pre-proc use time scale. Could you explain E the next question so I know I'm doing it correctly? What does E say, Ivy? I might have to, let me pull it down right here. What does E say? What does E say? Oh, there we go. You are doing the, here we go, classification. I took them all we used, we made in lab 7. There we go. Okay, I think I'm opening it up now. Let's see, will it open? Open. Here we go. So E, part E. Are you talking about this right here? Right here, this one right here, Ivy? Define the GLMNet grid. Is this correct for you right here? To the combination of alpha along the sequence of this, yeah. So looks like it's there. Run train to audition each of these models with the argument, blah, 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 together with the train control and pre-proc as defined earlier. Include a plot of the object created by the train to see how the estimated generalization has changed with the two parameters. Print to the screen the row with the best results. Component of the object that shows the best parameters and the estimated generalization are. How many models did the train evaluate? So pretty easy to see how many models the train evaluates. If this is set up all correct right here, define the GLM to have all the combinations alpha along the sequence, this through this, and lambda is 10 raised to this through this. So we have this right here. Blah, blah, blah. So we can see right here, 66 models are being evaluated. It looks like there's a, is there, this sequence right here, how many numbers does it have in it? Looks like 10. So 1, 2, 3, it's 11. So it's 11 and there's 6 things in this sequence. So this will be a sequence of 6 things right here. So there you go, 1, 2, 3, 4, 5, 6. So 6 times 11 is 66 things to evaluate. Oh yeah, we can do that one here next. We'll do that one here next, Tony. So there are 66 models being evaluated right here. And then what we need to do is this is going to be doing a GLM net grid. So this is a generalized, so we want to use an alpha and lambda tuning grid. So what I always do is I go back to here and we could do GLM net. And there it is. Boom, we're in GLM net grid. So what you want to do is you want to take this code right here, Ivy. So this is regularized logistic. Are we predicting a logistic? That's very important. I think this is logistic, right? It's classification. So since we're doing a logistic model right here and we're doing classification, we want to take and put this in here. If you notice, we've got our alpha lambda sequence just like before. We've got right here that we're putting a set seed to control the randomness. And then we're going to take the GLM net right here. And if you notice, it's y tilde x. We always like saying what our code does. Y tilde x is the variables we're taking, predicting y using x to explain, comma data equals, comma method equals GLM net. So it needs to be GLM net. Tune grid equals GLM net grid, which is this. Train control equals fit control. That needs to be set up beforehand to make sure you have the right fit control. We were predicting on AUC, so make sure to have 2 class factor summary, all that good stuff. And then pre-proc, center, and scale, all this right here. So the really good thing about having this cheat sheet is you can take this and just bring it over to your assignment and put it in here. Now make sure you have the right variables being predicted. I don't want to solve the whole thing, but this is a lot of the solve on this problem right here. We have done a good portion of the work. We can even indent it like it was a moment ago. Is that not going to delete? Well, I want it to delete. There we go. Now it's deleted too much. But, had so many spaces. Wow. There we go. And now we've got the, there we go. Much better. Just didn't like the way it was spaced out. But basically put in your y variable, then I think that's about it. All you need is your y variable, and that's set to go. Because the only thing, does that make sense, Ivy? Is it making sense what I'm grabbing for this, that I want to build a GLM net? All this is going to do is train and figure out what's the best model. Then once we save this GLM net, we're going to go right here. And we're going to go to results on it because this is a list. So we're just going to go inside and look at the results on it and find out what the best results are. Is this making sense, Ivy? Like once you store into that, you're storing into GLM net, and your GLM net becomes an object with things like lists inside of it, because you can put lists inside a list. So GLM net is just an object with lists inside of it, and you can look at the results and find the best results out of it. Is this all making sense? You can also use, we've got code to find the best list too. So if you look at it right here, here's the best tune, here's the result, and you could literally just take this right here and go into the results and go to the row name of the best tune. So I should practice writing these more often, but you can go right here and take that code. And as long as you know what that code does, this code right here is just going to get you the best tuned row. So it only returns the best tuned row right there. This code right here just returns the numeric value of the best tuned row because we find out the best tune, and then we find the row name of it, and then this is going to go to the results and return only the row, because like this is like 8. That's what it'll return, something like that. Or it could return like, who knows, like 34. It's just going to return the row name of the best row, and then we get all the results in the best row. How's this looking, Ivy? Is it making more sense? How's it looking? Then we're going to do the luring shoppers downtown one. That should be a pretty good help with that problem. They say y is a count. Is y a count? So no, it looks like y is purchase. Oh, is that an error in the thing? Because it looks like y is purchase, because if you look at this, here's the only categorical thing. If we're doing classification, is it saying account? I think I have something selected. Oh no, it's the account data. So it's account data predicting yes or no. So the variable is going to be, it looks like purchase, because we're predicting whether or not someone will make a purchase. That's the only categorical variable I see in there. So the variables, the data set is account, but the variable inside of it is purchase. And purchase is what we're going to predict because this is a classification model. Does that make sense right there, Ivy? How does it look on that? So the variable of interest here is purchase. One of my favorite functions, which we so rarely use. So, and do I have everything downloaded? Data account. Where is the account data set? It's a reg class. There we go. So one of my favorite functions we so rarely use, and we'll take a look at it right here. Anytime you load up data, make sure you do this. This is a huge key. A big thing when you load up data is to look at it. So you always want to have something you do to look at the data. And here's the account data right here. We could predict homeowner with classification models, but don't do it like that. Make sure to just put, once again, when you're doing this model down here, when you're making this right here, you would just want, is purchase capital? You would just want purchase right here. And then that's that, because it's training data. So you want to just put the name of the variable, and then the data frame is here. So we're going to make a train data frame, and then we'll use the train function. So this is an object, the train data frame, and then this is a train function to make a model using the train function in caret. Is that making more sense there, Ivy? We rarely, it's just when we do data equals, then we don't reference it by account. And once again, we're not using account because we're using training data. Once again, huge on predictive modeling right there. Always use your training data. So your models will be made from the training data. Your model will be selected on the validation. Then your model will be tested on the holdout. Yes, awesome. Thank you, Ivy. Great questions. Keep asking those questions if you have them. I'm hoping you just have to review this stuff. It's a lot of practice. I don't think I knew it super well the first time I learned it, and I did well in these courses, but you just got to keep practicing it. You got to be like, okay, why is this? Why do we do this? You have to keep asking. You got to be like, is it this? Why is it this? Yeah. Great questions. Remember, classification is always a categorical variable, so you have to look in the data frame. You have to say, we could predict the probability of someone purchasing. That's categorical. We could also predict whether or not someone is a homeowner. So my stat 1ers will know that. Tony is still here. We'll hop over. We'll do Tony's question. Tony had a question on the luring shoppers downtown confidence interval 1. Luring shoppers downtown confidence intervals. In an attempt to lure shoppers downtown, they open a parking garage. You're welcome, Tony. So let's see right here. Confidence intervals for the mean. Confidence intervals will be. I have super. Oh, this is a highlight of my quarantine, is that we might do some interviews and stuff. So put the word out there. Stat Tool 1 is looking to talk stats, and we're going to make some cool stuff for it. Like if we go over to Twitch, which we're planning, tell everyone, say, come check it out. Let's see if we can get our first stream on Twitch. Like if we get 100 people, I'll be happy. If we get 1,000, my mind will be blown. So wouldn't that be cool if on Twitch, the first stream, like, cause we'll do it like on a Tuesday night, and we'll do like an interview with like a professional baseball player. It's kind of our plan right now, is a professional baseball player who was in the World Series, understands the power of statistics, and we'll take questions from the audience, and it'll be interactive. So if we had 100 people, that'd be amazing. If we had 1,000 people, my mind would be like, whoa. But we'll do some cool backgrounds and stuff like that. I've got one right now, but we're gonna improve it even more. It's I have a green screen I need to set up, but like it'll look way better than this because this is not set up to look properly. Like it'll. I see, if I had the green screen, this might not look so bad right now. If I was green screening myself, it might look like, I'm a little too big, but I could make it a lot smaller. I could make myself, let me try this real quick. This is my one moment of fun right here. So let me see right here. Oh, it is unlocked. So I could be like right here, and I don't know, if I was green screened, it would actually be like I was sitting here. I just have to like higher up. But we could do this, and so this is the way we did it last year, but we'll see. So let me go back to the main screen right here. So we'll look into this. We'll see what's going on, and we'll make it look more professional than that, because I'll have my green screen, or we'll do like way cooler stuff. But anyways, let's do this problem right here. That's my like fun, like, let's do something fun. But tell everyone, be like, hey, let's check out this interview. No one has to, but I think it'd be cool. Okay, what assumptions must be made? So when we do this, my students know this pretty well. Condition 1, random. Condition 2, 10%. It means less than 10%. So we practice that. Condition 3, we pause, and then we think about it. And we say this is quantitative, so it needs to be nearly normal. So remember, condition 1, random. Condition 2, 10%, less than 10%. And then we pause because condition 3 will be different. And we have to ask, is it quantitative or is it categorical? And since this one is quantitative because it deals with the average they're going to make from these fees, then it's going to be nearly normal. So the data is randomly sampled. Good. The data is unimodal and symmetric. That's basically nearly normal. The data is at least 10% of the population. Nope, we want it to be less than. The data values are dependent. Now, if they were dependent, they wouldn't be random, so no. We need to make a 99% confidence interval, so you know what that means. It's time to practice our notation. Oh, I should make that. Abby would be very happy. A lot of people have been requesting the SpongeBob imagination since the start of the semester. That should go on my tasks for the weekend to make the SpongeBob imagination. So, like, I need to get that rainbow somehow and just be like, imagination. So, we need to make it happen. Okay. Fun things I'll try to do over the weekend. And so now we got our notation right here. I need your guys' help in the chat. I need to know what any of these numbers are. I need to know at least one of these numbers from someone in the chat. Brian is frozen until someone tells him a number. Wait, we need some Frozen music. Here's what Frozen music sounds like. Oh no. Who knows any of the notation on the screen right now? We need someone to help us out with notation. It's all about solving notation. Who knows any of the notation? We need one of these answered right here. We've got 42 is their sample size. That's got to mean something. 42 is their sample size. Is how many weekdays they collected. Mu and sigma. Which one's mu and sigma? I'll take that. I'll take mu and sigma. This one, well, close. This is going to be sample size right here. And so 42 is n. Now, if there's a sample size, not always, but a lot of times these will be y bar and s. Reason being is because they come from a sample. Now, this is not saying we know that they will collect 132 and we know the standard deviation is 12. In this chapter, from a sample of 42 days, we observed a sample mean of 132 and a sample standard deviation of 12. You got 1,000,000 points right there, Tony. I appreciate it. And it helps when you get things wrong to remember it. I remember so many questions I got wrong in class, and it helps me remember, like, oh, that's that thing. We have to, like, if it's the sample, so remember, this comes from a sample, so then this would be a sample mean and a sample standard deviation. Now, if this was for everything, like if it was for all data, then this would be the true mean and the true standard deviation. So when we have mu, it's the true mean for everything. It's like the GPA of all UT students is on average a 3.7. But then, that'd be really high. But then if we talk to 100 students and we get a mean, it would be y bar. If we said we talked to 100 students and they had a mean of 3.7, then that's y bar because that's a sample mean. If we say the standard deviation for all students is 0.3, that would be sigma. If we say we talked to 100 students and found a standard deviation of 0.3, that would be S because it comes from a sample. Does that make more sense there, Tony? Every time you see this notation, it's because they come from samples, but you were correct with mu and sigma in that mu means the mean for everything and sigma means the standard deviation for everything in the population. Don't worry, it's like the semantic part of it. It's the really hard part. I appreciate you being here learning, and we're going to solve this problem. Now that we know the notation, it's going to help us find the right formula, because we would have here that y bar plus or minus t star. We're going to have to find this t star with n minus 1 degrees of freedom. So how are we going to find us? Also, not a question. I forgot to submit extra credit for many ways. Yeah, go ahead and submit it. Go ahead and submit it. It's going to be large, but go ahead and submit it. Also, Tony, do you know about our exclamation point. Got the hiccups now. I'm so happy about this point system right here that I'm going to start using it later semesters, but we can't really It won't be how all your extra credits calculated, but I will look at it at the end of the semester. But you can look at your points that way too. I don't know if you saw that in the last few lectures, but I think it's so cool that tracks points. So we need to find T star with n minus 1 degrees of freedom. N minus 1 is the degrees of freedom. You bet. See how many points you got. And so the degrees of freedom right here is going to be 41. It takes a moment. It has to like go and talk to Streamlabs and say, how many points do they have? And so we need to take this and let's go. Hey, you got 50 mu bucks. They don't turn into real money. That'd be fun if they did. So now we need a 99% confidence interval. I'm going to drop this link in the chat here. So I'll look at them at the end of the semester. And at the end of the semester, they'll be part of your extra credit. Like, it won't be all of it. You'll still get it the normal way I'm doing it with like 10,000 ways. A lot of opportunities to get extra credit in this class. But if someone has a lot of mu bucks, I'll take that into consideration. How do you get mu bucks? You talk in chat. It's like if you talk in 5-minute intervals, you get 5 mu bucks. So every time you talk, like after a 5-minute interval, so if you talk like a whole bunch right now, you won't get another 5 mu bucks. It's like you get 5 mu bucks for talking in chat in different 5-minute intervals. So once you talk, if you talk then 5 minutes later again, you'll get another 5 mu bucks. So it's just like who's interacting in chat. The more you interact, the more points you get. So you could technically put a timer for every 5 minutes and be like, hi, and it'd probably give you the points. So if I saw someone just saying hi every 5 minutes, I'd be like, are you trying to get free mu bucks? But if you just watch the lecture and interact, you'll get the points. Andrew, check your points. Check Andrew. I wonder what Andrew's at. Andrew's been here. Andrew's came to multiple live streams. It only works on the live streams when I'm broadcasting to the public. That's part of the issue. I think it just doesn't work when we do it the other way. So you just started. That's awesome. Good to see you, Andrew. So Andrew has 100 mu bucks right there. The top getters right now have like 300 or so. 2.647. So, and I put that link in the chat to show how to get the T. Then now we need to go plus or minus. That's the T right there. And let's remove that arrow. Arrowed. No one knows that reference anymore. 12 over square root of 42. Oh, did I put in? Nope. I think I got a problem, everyone. I think I put in 71. I did. Okay. And it changes that. Is it 99%? 2.702. Wow. This is where my brain starts to fade. 2.702. Let me make sure it's 99% too. Sorry, that was an error. 2.702. Cool. There's a way I can add you points. 42 is n. You are right. So degrees of freedom are 41. John, amazing work. It's so easy to make mistakes on these. It's so easy to like get the number just mixed up in your head and then put the wrong thing in there. So I'm going to copy this into the chat and you guys can use that link there. That'll bring you to literally the picture I just made right now. But this is a 99% confidence interval. And we want to go back to brain is breaking. Cool, 99%. So we just need to solve the equation right now, right here. So let's start solving it. And here we go. 42 square root 12 divided by, boom, got it, times 2.702, got it. Now, what did I just find? Yes. I like that number. I like that number. Someone's got to tell me why I like that number. We're going to do the rest of the problem in our head. Can you do the one in chapter 15 of the States? Yeah, we'll do that one next. Awesome, Amber. We got that one next here. Thank you for being here, everybody. So what did Brian just find? What did Brian just find? And why is he very happy about that number? That is amazing. That is an amazing, beautiful number. Watch what I solved. I solved everything right here. What did Brian just solve for? Everything from here over is the what? What is that? What is everything after the plus or minus? The margin of error. Tony, amazing work. 100,000 points right there. You got it. It's the margin of error. So guess what? We're giving away a million points today. Why not? It's 5. So as long as I did all my math right, that's easy to do. We got that in our head. We're good. So we're going to go back to the question right here. We're going to try to get it right in our heads. It's just 132 plus or minus 5. Explain in context what this means. We are 99% confident the interval contains the true mean. It's not that it falls, it's that it contains it. Explain what 99% confidence means. 99% of the intervals, 99% of 99% intervals contain the truth 99% of the time. So 99% of all sample sizes 42, let's see, it's getting tricky right here. It's going to be one of these two. So contain the mean daily. 99% of the sample size 42 produce confidence intervals that contain it. Yep. It's not that these will have means that are inside the confidence interval. We make confidence intervals and they might contain the mean. Such specific wording right there. So it's the theoretical stuff we should know is a 95% confidence interval will contain the true mean 95% of the time, or 95% of 95% confidence intervals contain the truth 95% of the time. It's theoretical, saying that in the long run, if you kept making intervals, 95% of intervals will contain it. Not that one interval has a 95% chance, but that theoretically speaking, in the long run, 95% of 95% confidence intervals contain the truth 95% of the time. It's a little tricky. Once again, let me just say it again. It's not that one interval has a 95% chance. It's the law of large numbers that if you kept making these intervals, 95% of your 95% confidence intervals would contain the truth, i.e., in the long run, 95% of 95% confidence intervals will contain the truth 95% of the time. Woo! So, there we go. Since the 95% confidence interval, what is it? They said 129. 129 is in the interval. So here's one thing. Please notice these questions are not always the same. I looked at 129 and then I looked and said that is in my interval. So the consultant's prediction is plausible. So they're saying 129 is a possible value. 129 is in my interval. So it's good. Now, did Brian do his math correctly? Yes, he did. At Streamlabs. I don't think Streamlabs can respond to you. That's pretty awesome right there, Tony. There might be a way. Here, Tony, I'm going to try to do this real quick. I'm going to try to add you points on Streamlabs. I think I can maybe do it. Let me try. No, I think these commands only work in the Twitch chat. Streamlabs. Okay, let me try to add points to people. I'm going to try this because even I want to learn more about this. So, why can't I highlight that text? Example, plus points, add viewers. Okay, so let's try this. Points, add viewers. Okay. I'm going to try to add 100 points to people. So points, add, plus, viewers. So is it plus viewers or... And then let's add 100 points here. Lowercase viewers, it looks like. I don't know if that did it. It'd be honored. So I don't know if that did it. Tony, check your points again. I don't know if that added points. Oh, no, you see, it's just checking my points. It's merely not, it didn't add points to everybody. It just checked my points. Yeah, it's supposed to put a thing in the chat that says giving 100 points to everyone in chat. Now, I bet you I can do this in over here. I'm going to try the same thing I just wrote. This is my test right here. I'm going to do it over here in... Oh, it's not working over there either. I just typed it in Twitch. It says points add. Oh, darn. Can I click editor? No. Make sure you use replace points where you want to... Well, maybe... It might be Mubucks. How many was Mubucks KBS? Like, I'm still learning these things here, too. But what's weird is, over on Twitch, I have 0 Mubucks. So it looks like it keeps different points on different systems. So the more I learn about this, the better. But it's just trial and error for me right now, like, figure out what's going on. And I don't know why I can't I think Streamlabs is set up for, you see like you have 5 more points now, so it's like on 5-minute intervals. So it looks to be working kind of properly. I might like a different bot or something. And then there's channel points on Twitch also. So we can literally just do channel points, but people could buy stuff with those. So channel points would work also. Chat commands. I think we had another problem. What was the problem people wanted me to do? I'm lost in all this right here. Vanished, last seen. I think you can do like... So, yay! Wait. Last thing, and then we'll take the question right here. Watch this. I have another way. There's always a way. I know of a way. Watch this. So, so Tony, I want you to check your wait. Oh, maybe I gotta do capital? It says there's no users that match your name. What is going on? Let me try this. How many $bucks are at? And then we'll do the problem right here. Tony is at page 1. And then Tony's at 55. Let me see if I can find you in the list, Tony. Oh, a lot of people are at a lot of points. Let me see if this does it. There you are. All right. And I wonder why I couldn't find you. Oh, it's... Well, wait a minute. No, I clicked the wrong one. All right. Here, wait. Andrew said you got his points. There we go. Tony, check your points now. So, Tony, check your points again. Have you seen all the discounts for Coding and Hangout? I was thinking about buying it and trying it. I haven't seen that yet. So, if you notice, we got quotes in there and stuff. So, people can actually put quotes in here. So, but yeah, so Tony, your points should change. There's ways I can change it. Code Monkey. That's so crazy. That's crazy. There you go, Tony. New Mew points for you right there. Okay, so let's continue on with the question. The question was, can you do the vital statistics? And that's a conference roll one, I believe. So let's do that right there. This is our fun for the day. So we're about to have another timestamp in here if someone wants to timestamp it, where Brian works another problem. And I love it. Little people checking their points. Is this a conference roll one? Oh, it's chapter 15, right? Okay. Sorry. I'm going to pull it up right here. It's chapter 15. I was in chapter 14. Let's see. Is it homework or quiz? Homework or quiz, Amber? I think it's a quiz. So let's take a look here. Mouse. Why you do? And let's bring it here. Vital statistics. 1. Remember, we're going to do our 4 steps here. When this problem comes up, I believe it's conference roll. So we're going to do our 4, not conference roll, doing it. Here we go. It's a statistical test, so we need our 4 steps for statistical tests. Cool. We're going to make it nice and big right here so everyone can see what's going on. And let's do the 4 steps for statistical tests. We're not even going to read the My Pearson question. We're going to do the 4 steps on this. You ready? Here's your practice. So if you're following along with me right now, make sure you know the 4 steps for statistical tests and practice them with me as we do this problem. We'll make this font smaller. And then we go over here. We open up a new worksheet. We drop it in here. And here we go. So you guys are awesome in the chat. So we go right here. And we start with figuring out our notation. So I'm going to give you this one away because there's we're going to work on this and get it done and do maybe another problem. We got enough time maybe. So let's take a look right here. And we see this, this, and this. You guys only need to tell me what is the only thing in here we're not going to use for notation. What is the only number I highlighted that we're not going to use for notation? And so, the same. There we go. What is the only? You're right. You got it. That's the only one we're not going to use for notation. Nice job, Andrew, right there. So you're going to earn more mu bucks. I should delete yours and then you still got yours. I want you to have yours. So this right here is the hypothesized true proportion, because that's what we're going to test against. This right here is the sample size, and this right here is the x. From x over n, we're going to get p hat. And so p hat is equal to something like, what is that, 7.4%? No, it's going to be, oh, my brain is so bad at this today. That's going to be like 2.8%. 2.8, I say. 2.8%. How close was I? 2.8. Almost 2.7%. So 2.7%. So 2.736. Okay. So that equals 2.736. There we go. And 2.736 as a decimal, or as a percent, and this as a decimal. So we have the proportion right here, x over n, and we also know p naught. Now we're going to start doing the solve of the problem right here, writing out the notation. Step number 1, write your null and alternative. Practice this. Every time you see me doing these problems, pause the video and be like, okay, I got to write that null and alternative right now. How do I do that? Start by writing the null. We're going to do it this way today. We're going to write our null, the true proportion, because we're testing a proportion. We're seeing if the true proportion is equal, because the null always has the equal sign, to the hypothesized true proportion. The hypothesized true proportion is 0.32. Now, once we write our null, we can carry down everything we just did and only change that sign. If you noticed, I highlighted this right here because it's either the same or it's not the same, like Ben Folds would say. So we have right here, step 1 is done. Step number 2 is going to be to solve the equation. We need to know the right equation. We are using a 1 proportion z-test. So here's the equation for the 1 prop z-test. It's going to be p times q over n square root. There's our classic p times q over n square root. I'm going to zoom out a little bit so we can actually see the right here. That equals z. So Ben Folds 5, you got it. Have you ever listened to Not the Same live? So just type in Not the Same live Ben Folds. He conducts everyone like an orchestra. It's one of my favorite live experiences. So Mr. Ben Folds 5. We need P naught, right? P hat right here. P hat. So 2. That's a 2. How many songs can you name by Ben Folds 5? You gotta be careful because then there's Ben Folds songs. The older I get, I'm like, man, like, and then Ben Folds getting really old. We're all getting old. This is the way it goes. I'm not old. Who knows? And so this is P naught right here. This is Q naught. We're running out of so little room. 9, 6, 8. They have to add up to 1 just to make sure everyone knows that P naught and Q naught are complements. So you just take P naught, subtract from 1. So I was doing that in my head right there. Just thought 100 or 1,000 minus 32. A lot of ways to do it in your head. But that is it right there. And then we put the n on the bottom of this. And so this has given us the answers right here, and this is going to solve for z. So this will solve for the z-score, which tells us how far this is away. So we're going to get the z-score right here by doing the bottom first. Got to remember that. You don't have to. It's just the way it works in this calculator best. And that's that right there. Hopefully you did it right. Square root. Don't forget your square root. And then it looks like the z-score is going to be pretty small, like negative 0.8 or something. See how close? That was a quick guess, so probably pretty far off. Hopefully I don't do this too quickly and make an error. Negative 0.528. And I always get, if people wonder, why does Brian always guess? Because when I take a guess, I'm kind of figuring out what it might be. I'm kind of looking at it mathematically. And if my guess is very close, I think I probably did it correctly. If my guess is very far off, I'm like, oh, I probably punched it in the calculator wrong. So I always take a guess to see if what I punched in the calculator is pretty accurate. So negative 0.8 was my guess, and it was a quick guess, but still looks to be about, it's close enough that my guess was like, okay, I guess I got kind of close. So negative 0.528. Now, if I did put in a guess of like imagine if I were to guess, and that might have rounded up. It does round up. So that's a 9. Just imagine if I had guessed like 62 and this was the answer. So I was like, that looks about 62. And then I got this answer. I'd be like, wait a minute here. Did I do it wrong? Or did I, and I would double check my math. So every time my guess is way far off, I double check my mathematics. So that's the z-score. We need to now plot the z-score, and this is also, I'm going to take a guess at the p-value on this. So the p-value, I know some numbers that a lot of people don't know about the normal curve, some secret numbers. I know that right here at about 2/3 of the way down is 25%. So if I know here is 25% at a z-score of, and maybe I shouldn't put this on here because people start watching this and get very confused. I know right there is 25%, but we're not there. We are over here. So if 25% is further over, this has to be more than 25. So I'm going to say it's about 30. That's a really quick guess, but I'm going to say this is about 30% of the curve. And let's take a quick look at it. 30% is probably close. Someone better start calling me out on this, because this is not a one-tailed test. This is a two-tailed test. So the answer is not going to be 30%. We'll put some red lines here to make it clear that's where we landed. And then this one is the reflection of it on the other side. The p-value I want to see in the chat is not going to be close to 30%. The p-value in the chat, someone's going to help me out here. It's not going to be about 30%. That's 30%. The p-value in the chat, what is it going to be? The p-value is going to be close to about what percent of this curve? The p-value is going to be very close to about this percent. If I'm guessing that on the left is 30%, the p-value is going to be close to about what? What will the p-value be close to? 60%. Nice job, Andrew. Amazing work. Andrew, great job. You're great job. Let's go grab that z-score. Brian says it's 60%. So nice job, Amber, right there. 1,000 points, million points for everybody. And the answer is we got to turn these into z-scores again. Wow. Look at that. That is so close to 60% right there. That is right at 60%. So we had a really good guess on that one. So we were very, very close on our guess, and that probably means we've done everything correctly. So now the last thing we have to do is we have to reject or fail to reject the null. So our p-value is high, just let that null what? You just got to type 3 letters in the chat. The p-value is high, just let that null what? That p-value is high, just let that null what? I'm going to start writing this here. I want to see in the chat. The p-value is high, just let that null fly. You got it right there. The p-value is high, let that null fly. That means do not reject. That means we do not have evidence. We do not reject the null. We do not have evidence. Fly right there, John. Nice work. We, million points, everyone. Just crazy points. Who knows what's going on? I promise you, come to class, interact. I will be giving out lots of points. I'll be very nice with the extra credit at the end of the semester. You just have to come to class. You have to interact. That's what I ask of people. Come to class, interact. I'm going to be very nice with the extra credit. And I can look at Streamlabs to see, like, if someone's like, Brian, I was in class all the time. I'm like, no, Streamlabs said you're never here. I don't want to do things like that, but I trust you guys to come to class and interact. So we've got all the problems solved right here. Remember, we were seeing if it's not equal. We've got the z statistic right here. We've got that still in the calculator right here. So we're just going to copy. We're going to drop it in. We're going to delete down decimals. We've had a perfect streak today. We haven't gotten a single problem wrong. The p-value is 2-sided. It's 3 decimals, so good thing we entered it in. Okay, I'm gonna wager our perfect streak on this. It'd be wrong if it's gonna want the 3 decimals. I can't wager the perfect streak on this. We're going flawless today, so I can't wager it. I can't wager it. We got to get it right. What is the conclusion? Fail to reject, because this is fail to reject. Anything else after that has to be right, because there's only one fail to reject. If the p-value is below alpha, which it doesn't even specify in alpha, which is probably 0.05 if not specified, when the p-value is low, reject the null, because that would mean what we saw was unlikely due to random chance. Think about this. What did we see in our sample? In our sample, we saw that 2.7% of these young teen mothers were having twins, and then national statistics report that 3.2%. So do you think this might just be random variation? It's like this. Imagine your friend tells you that they can run a 6-minute mile, and then you see them run a few miles, and on average they do it in 6:03. Would you be like, you're a liar? You said you could run 6-minute miles, and they're like, well, I ran them in 6:03, and you'd be like, nope, that's enough evidence. I reject that you're a 6-minute mile runner. Would that be good? Would you be doing good statistics? Be like, I mean, just think about it. They say they can run a 6-minute mile. That's the claim. And then you see them run a few miles in 6:03. Like they run like 10 miles separately in 6:03, like 6:03, 6:01, 6:08, 555, but the average was 603. And Andrew knows you would not reject the null. But what if your friend claims to be a 6-minute mile and you secretly observe them running miles and they're running their miles in 15 minutes? So your friend's like, I can run 16-minute miles, and then every time they go out to run miles, they're running them in 15 minutes. And apparently they're trying. Like, they're not just jogging for fun of it. They're like, I'm really working hard. I'm running a 6-minute mile. So every time they say they're running a 6-minute mile, they run it in 15. Think about that. Would that be evidence against their claim? Would that be strong evidence? And would you be able to reject that they're a 6-minute mile runner? Yes. You'd be like, that is strong evidence. That example would look like, when you draw it out on the curve, if they're a 6-minute mile runner, if they start running their miles in like 603, 601, I know 15 minutes like a walk. So they would land here. Well, we can draw this better. If they were to do something close to what they claim that would seem likely by random chance, then here's where 6-minute mile is. And then if they were running around here, then this might be like them running 601, 602. We're not solving all the math on it. But tell me, 601, 602, could that occur probably by random chance? Just without the statistics behind it, would that possibly just happen by random chance? If someone's a 6-minute mile runner, might they run their miles on average in 601? Like if we were to like observe them run a bunch of miles, would that seem plausible? Like we'd be like, yeah, I would continue to believe that they're a 6-minute mile runner. And the answer is yes, we would continue to believe it at this point. We would be like, okay, I still believe you're a 6-minute mile runner. But if they were running their miles in something like 15 minutes, which is like a walk, they'd be way off the chart over here. And I want you to tell me what the p-value is. I want someone to tell me what the p-value is on this. What is the p-value, which is the area above our result, a result of 15 or more extreme? What is the p-value on that? It looks very, very close to what? What is the p-value? And that'll help you understand what is this whole thing with p-values. It's saying, given someone is a 6-minute mile runner, observing them running their miles on average at 15 minutes or more, see how this is 15 minutes or more? Observing them running their miles at 15 minutes or more, given they are a 6-minute mile runner, should occur around, who knows the p-value right here, it would occur around what percent of the time? Given someone is a 6-minute mile runner, observing them running their miles, and let's make sure we scroll down. I don't want to think that's not reject. That is so reject. I'm going to erase that not reject. We would so reject this null. Way bigger than 3 standards. P-value of 0. Yep, that's exactly Andrew. Nice work. That is a p-value super close to 0. It'll be like 0.000001 or something, but it's basically 0 or small enough that we would definitely reject. And think about this. At this point, you would have so much evidence that someone is not a 6-minute mile runner. They'd be like, yeah, I ran my mile on average in 15. And they'd be like, I'm a 6-minute mile runner. You'd be like, no, that's so much evidence you're not a 6-minute mile runner. I have extreme evidence to reject that null. I have reason to believe you're not a 6-minute mile runner. I reject my null. I have evidence that your true mile time is greater than. Notice how we're shading to the right. I have evidence that your true mile time, and this null and alternative would be null that their true mean mile time is equal to 6 minutes, and alternative true mile time is greater than 6 minutes. So I would have evidence, look at the way I shaded right there to the right, I would have evidence that their true mile time is greater than 6 minutes. That's got it. Let's see if we got that question right. All this good stuff right here. Did we get the question right? The answer is we did. Awesome stuff. So in BAS 320, we look p-values less than 0.5. Yet in this class, the p-value closer to 1. No. Always low p-value is more evidence. P-values, the lower they are, the more evidence for the alternative. So we always look at p-values less than 0.05. Well, that's the general guideline. But the lower the p-value, the more evidence for the alternative. And then alpha is what you can kind of change to say how much evidence you want. Alpha is the degree of evidence you want, and anytime p-value is lower than alpha, you reject the null. Alpha is often set to 0.05, which is just usually what we call statistical significance. So by default, we assume alpha 0.05 unless otherwise specified, and when p-values are lower than alpha, we reject the null, and we have more evidence for the alternative the lower it is. Does that make sense, Andrew? I can explain in greater detail or free for asking any questions. My hair is getting crazy. It's... Like, however long this quarantine goes on, I'm like, should I just, like, not shave and not cut my hair? By the end of quarantine, I'm just going to be, like, bearded and, like, hippie hair. So, it's crazy. A little, yeah. Delve deeper if you want. I'll hang out for just a little bit more and then hop off. I want to look at... I think we had some good amount of people in here today. Where is the stream? We have 10 viewers right now. Wow. And we got up into the teens. That's good for a random Friday stream. So good stuff with all the people here working some problems. Put timestamps in the videos. It helps out everyone. I think everyone, I know I can do it too, but so many things. About to start doing the test grades after this. But feel free to email, and Andrew, feel free to ask any questions if you want for help. Appreciate you guys. And I know we're trying to make sure all our classes in the whole department are really, everyone's getting help. So, you're welcome, Julian. We're finishing up now. I appreciate everyone. Yeah, just here. We just did a last question. Throw some timestamps. Did anyone make 100 on the test? I think there was like, I'll have to look across all sections. I think we had a 90. I want to say we had a 98. And I was like, holy mackerel. Yeah, I think we did, because I think someone's going to have 101. So I was like, even, wow, that's really tough. So, it was a tough test, I will admit. And just, it's easy to make a mistake or misread a question. So, once again, the averaging, I think, is a huge help. And then the average for the class is like I think we have like a 81 average or something like that. So the average is really good. So, the average is like an 81, and there were some people who probably got a grade much lower than it's tough, because it's like, maybe you've got tons of students working really hard, and a lot of them it will pay off, and then some maybe just will have a bad experience with the test, because everyone has a bad test every once in a while. So we want to help, and that's why we're doing the averaging again for the final. That's why I'm doing all these streams to help with the quizzes, because if you get a really good quiz grade, you can average 100 with your test. So stay motivated, keep working on these quizzes. I'll keep being here to help out, because if you can get 100 on the quizzes, that'll be a huge help for your average, because you can then make if you make a 70 on the test, you make an 85, because you averaged into their 100. You make a 60, which no one really wants to make a 60, you still make an 80, you still make a B. You make a 40, that wouldn't be fun either. You still make a 70, which is a C. So the averaging of the 100 will stop anything. You like the format? Cool. I'm glad to hear that. We worked on it really hard, and it's impossible. Like I say but Dr. Panel, Missy, and Terry they did a ton of work, and I really appreciate it. Dr. Panel especially, not that anyone else didn't do a ton of work, but he kind of led the way, and he was a big part of it. So I'm so thankful that they worked so hard on that, because I had a lot of things going on, especially with 474 and everything. So I really appreciate and I appreciate the students' understanding too. We're always here to help. I think everyone knows that we are the Stat to One team, and the whole university is stepping up for everyone. And I want people always just to reach out to me if there's an issue. We're trying to be as understanding as possible, and we're trying to be as understanding as fair as possible. That's as best I can say. So we're just doing everything we can, and we really appreciate you guys and gals. So it's so good. You guys made me so happy. So I think that's got it. We did a lot of questions today. That's got the online hours. Find a time that works for everyone. We're gonna start doing the Twitch thing probably next week. I'm gonna try to set up the studio. That'll be really fun. I'm just going to have to rearrange this whole room. It'll be pretty crazy. But I think that's got it for today. We'll end the way we started, with a little SpongeBob. I'll see everyone later. Bye, guys.
Here's one thing about it. You can just go up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You know, it's just in the chart title, it's all this stuff. Yeah, also, I'll show this again real quick. Look at all these options. We got so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.